In this video, we're going to look at similar triangles, and in similar, or also known as equiangular triangles, all triangles in one triangle have the same measure as the corresponding triangles in the other triangle. So if I label this side 1 here, this equivalent side over here will be this one. This side here, 50 to 70, will be this one. So these sides are in proportion. Okay. So the converse of this theorem is also true, which is if the sides of two triangles are proportional, then the triangles are similar. And what they're saying here with these three statements, if xy, this guy over pq, if that's equal to yz, this one over this one, and if that's equal to xz over pr as a ratio, then the triangles are similar. So let's have a look at a question in relation to this. So in the following diagram, AB is parallel to DE, and we're asked to prove that these two triangles ABC and DCE are similar. So the top triangle is similar to the bottom one. I'm just going to put my Z in to begin with here, and we'll get our alternate angles. So which angles are alternate? This one and this one must be the same due to alternate. We also have this one and this one are the same due to being opposite. Now you would write these words out. I'm not going to write all this out, but that's what you're going to write out, and you give them the letters. And then the top one also is alternate. This one with the Z going this way is alternate to this one. So if I take those two triangles separately, and I write A, B, C, and I number them. The blue one is 1, the red one is 2, and the green one is 3. And I write my other triangle and do the same. My red one is number 2, my blue one is number 1, and my green one is number 3, and we have C, D, E. So the proof of the similarity is the two alternate and the vertically opposite angles in the middle. So what values do we have? We have CD being 10, we have AB being 7, AC being 3, and BC being 5. And we're asked to find DE, which we'll call X. So starting with our unknown, angle 1 to 2 on the other triangle is my 7. You can see angle 1 to 2, we're matching up the sides with the angle numbers. So x over 7 is equal to, well, I have 10 is the only thing I have here between angle 2 and 3. So that's equal to 10 over between angle 2 and 3 on this side is my 5. So 5x equals 70. X in this case will be 14, which is equal to DE, 14. AE, okay, I'll move up here and do it. AE, let's have a look. AE is the big jump, so from here to here. So we need CE, we'll call it Y. So Y over between angle 1 and 3, I have 3. That has to be equal to 10. I could use the X as well, I'll just use the 10 between angle 2 and 3 over 5. So 5y is equal to 30. So y is equal to 6. So the full length, this becomes 6. So AE becomes 6 plus 3, which is 9. Now, a real life example of this theorem. We have this man 1.8 meter tall, and we have this length of 5.6 meters. In this triangle, we have 22.4. and we have x. So we want x. What's that similar to in the other triangle? It's similar to 1.8. So that has to be equal to 22.4 over 5.6. And I'd have to multiply 22.4, or I'd have to multiply 5.6 by 4 to get the top. So I multiply this one by 4. I'm going to get 7.2 is equal to x, or cross multiplying 5.6x is equal to 22.4 by 1.8. So x, simplifying it down, works out to be 7.2 meters in this case. And we could put the person inside here, and that's how we'd end up with similar triangles. We have a right angle. This, if I take the small triangle, this angle here is the same as if I left the big triangle alone. So I have a right angle and an angle the same, which means that this third angle must be the same. Therefore, the triangles are similar if you were asked the proof of it. So go on and practice some questions with similar triangles.